We're going to look at the third rule for differentiation now, which is the quotient rule. So this is the last one that we need to, this is the last one that we prove this way. So we want to show that if f is u over v, then the derivative of f is given by this formula here. Alright, so it's v times the derivative of u minus u times the derivative of v all over v squared. Just one or two things to say. The first thing obviously is that for the product rule, it doesn't matter which one is u and which one is v. For this one, it does. U has to be the top line, v has to be the bottom line. Obviously, if you swap u and v here, you get a completely different formula. Second thing, just to mention again, is that u of x is just saying that u is a function of x. So if I put in different x values, I get different values for u at the end. That u bracket x bracket, u of x, is the same as the u there. I just haven't bothered writing in the bracket with the x in it. Okay, so this is still u of x. We just, I guess for convenience, inside the formula, we just write it as u. Okay. Again, that f dash x is the same as df dx. Alright, and that v is the same as v of x over here. Alright, so u du dx, we could have written that as u dash x. But I think this is the way the formula is in the log table, so we might as well just write it out this way. Okay, so let's go prove it. So as ever, we start off and we say that f of x plus h is going to be u of x plus h over v of x plus h. So that's grand. So then the top line, f of x plus h minus f of x. The top line of our, sorry, I guess I should really have written in over here, f dash x equals the limit as h tends to 0 of f of x plus h minus f of x all over h. Alright, so there we have our differentiation from first principles formula over there. So this is what we're filling in. Sorry, so that's where the f of x plus h came from. So we've filled in this bit. Next we're going to fill in the whole top line. So that's f of x plus h, which is u of x plus h over v of x plus h. Take away f of x, so minus u of x over v of x. Okay. We might as well get a common denominator here. So our common denominator is going to be vx plus h times vx. And you can hopefully see now where the v squared on the bottom line is going to come from. It's going to come from this times this. Because if h is 0, this is just v of x by v of x, which is v squared. Alright, so that's where the v squared there is going to come from in a while. So our top lines, this was u of x plus h. And then now I've multiplied this bottom line by vx. So I better put that by vx. This was u of x. I've multiplied this bottom line by vx plus h, so I better do the same to the top. Alright, so that's what we end up with. Okay, so let's divide that by h, which will mean putting a h in on the bottom line. So we're trying these in landscape, see how they work out. So, therefore, f of x plus h minus f of x all over h is equal to, so u of x plus h times v of x minus u of x times v of x plus h, all divided by h times v of x plus h times v of x. Okay, if you're dividing a fraction by h, you can simply put the h in on the bottom line. Alright, which is what we've done there. Now, as in the previous, as in the proof of the previous rule, the problem here is that if I get the limit as h tends to 0, if I just fill in h, right, so h as 0, so ux plus h is going to become u of x, vx stays as vx, ux is going to stay as ux, vx plus h is going to become vx, and on the bottom I'll have 0 times v of x by v of x, so 0 times vx by vx. And once again, ux plus ux by vx minus ux by vx is 0. The bottom line is 0 by something which is 0, and this is indeterminate. Okay, it's not just undefined, it's indeterminate. So I don't know what it is. I don't know if the limit exists or not. So this is why I'll have to do a bit more work. So let's go right down lim equals, and we'll decide what we're doing. So the limit as h tends to 0 of f of x plus h minus f of x all over h, which I guess we should say is f dot x. So that's going to be equal to the limit as h tends to 0 of ux plus h times vx minus ux times vx plus h all over h times vx plus h times vx. Alright. So, once again, we're going to add and subtract something. We've got to decide what would be the best thing to add and subtract. If you have a think about it, our first term here, the term at the start, we want to have v times du dx. So if we want the du dx at the start, that means we want a ux plus h minus u of x. Alright, if we look at what we're aiming for, so let's give ourselves a bit of room. Tends to 0. Ux plus h by v of x. Now we want minus u of x. Alright, we want du dx, so that means we need ux plus h minus u of x. We need to be able to factor something out from the two of these, so we better put a vx there. Alright, so now we can factor out a vx and we'll have ux plus h minus ux. Perfect. Because we minus this, we better plus it, so ux times v of x. And then we still have that other blue term, which is minus ux times v x plus h. And the whole thing is divided by h times vx plus h times v of x. Alright, oh, that's a bit cut out. Sorry about that there. So that just about fits in there. Alright. So we put this in because we were looking at the answer. We know we want the derivative of u, so we want ux plus h minus ux. We need to be able to factor this term out here, so we better put a vx here as well. Okay, and what will happen here now is there's a ux common, so we'll factor out a u of x, and we'll be left with, well, if we factor out a minus ux, we'll be left with vx plus h minus v of x. So let's go do that. The other thing that we're going to do here is notice that the vx plus h times vx on the bottom line, that doesn't really come into the derivative part. So we might as well get that outside the limit. There's no point in leaving that in under the line. The h is all we want under the line for the derivative part. So let's take the limit of this separately. So as h becomes 0, this becomes v of x times v of x. Right? So the limit of the whole thing is equal to, well, it'll be 1 over vx times vx. That's going to give us our over v squared. So what we did there is, look, we said on the bottom line we have a vx plus h times v of x. Let's get the limit of that bit, because that won't really interact with anything else. So let's get the limit of that bit. So that's going to be 1 over v of x by v of, the v of x stays the same. The vx plus h just becomes v of x. Alright, times, okay, we're considering this first of all, so these two terms here. So it's times the limit as h tends to 0 of ux plus h times v of x, grand, minus ux times v of x all over h. So that's the first term. Okay, the second term we get from considering the second half here. Now, because our formula has a minus in the middle, we'll probably want to say minus. So minus the limit as h goes to 0. So if we take a minus, then this is going to become, well, this one will be u of x times vx plus h. And this will become a plus, and this will become a minus. So minus ux times v of x all over h. Alright. So just to kind of go back over there just to check, the 1 over vx plus h vx, we took the limit of that and just brought it out to front because it's common to everything. We've got a big bracket now. We're multiplying that into. We have the first two terms, put them over h because that's what's left on the bottom line. For the second two terms, we know we want the minus in the middle. So minus this term gives me that there at the end, and a minus by a minus gives me plus this term here in the middle. Okay, and we're set up now to finish it. So that's 1 over v squared at the start. So I should put an equals up there. So that's 1 over v squared at the start. There's a v of x common here, so let's factor that out. So that's v of x times the limit as h tends to 0 of ux plus h minus ux over h, minus, there's a u of x common here, so let's factor that out, ux times the limit as h tends to 0 of, not sure if we're going to fit this in, so vx plus h minus v of x all over h. Alright? So, when we take those limits, this is 1 over v squared times vx, this is du dx, the derivative of u, minus u of x times this, which is dv dx. So to rewrite that another way, we will get v of x du dx minus u dv dx all over v squared. And that's what we were looking for. So a little bit squashed, but we got there in the end. So just to recap quickly on what we did, we filled in the formula. We said that if we take the limit now as it is, if we sub in 0 as it is for h, we'll end up with 0 over 0, which is indeterminate, so that's no good. We need to subtract and add, or add and subtract something. Take a look at what you're trying to prove. So our first term here, we want a du dx in it. That means we will want ux plus h minus ux. So ux plus h minus ux. We do have ux plus h minus ux, but it's no good because we can't factor, these two terms aren't common, so they can't be factored out. So we need ux plus h by v of x minus u of x by v of x, factor out the v of x's. Because we minus it, we need to plus it here. And keeping again an eye on what we want to prove, we know we want the minus in the middle, so we'll have minus bracket this thing, take away this thing, and then we see there's a ux common there, so we take that out, we'll end up with vx plus h minus vx, which is exactly what we're looking for, because that's dv dx.